In this section, we're going to explore all the different ways we have to represent a linear system of equations. So I have here a system of linear equations that we can use as an example. Okay? Now, we've seen that another way we could represent a linear system of equations is as a linear combination equation. So here I would take the coefficients for each variable as a vector. So for x, that's 3, -1, 2. And then the variable is the scalar multiple of the linear combination. So x times vector 3, -1, 2. For y, the coefficients are -2, 0, 1. So I have plus y, -2, 0, 1. Plus, now for z, my coefficients are 4, 5, -1. So plus z times vector 4, 5, -1. And for variable w, my coefficients are 1, -2, 3. So plus w times the vector 1, -2, 3. And that is equal to what's on the other side of these equations, 6, 1, -4. So we'll have the vector 6, 1, -4. So this vector equation, this linear combination equation, is equivalent to our linear systems of equations. If we look component by component, we get the same thing. 3x minus 2y plus 4z plus w equals 6. 3x minus 2y plus 4z plus w equals 6. It's the same thing. Okay, so that's the first equation, the first row of my linear combination equation, but it's true for all rows, all equations. It's just a different way to express the same idea. Okay, but we've also seen that we could think of a linear combination, express a linear combination as matrix vector multiplication. And so we can also write this linear system in matrix form. So matrix equation. So here the matrix is the coefficient matrix of the system. The columns of the matrix are the vectors in the linear combination that I'm taking the linear combination of. So column 1, 3, -1, 2. Column 2, -2, 0, 1. Column 3, 4, 5, -1. Column 4, 1, -2, 3. And then we're going to multiply that by our vector of variables, by the scalar multiples of our linear combination. So our variables x, y, z, w. And based on what we know about matrix multiplication, this matrix product is going to equal to this linear combination. Remember, this x gets multiplied by this column. The y gets multiplied by the second column. The third variable z gets multiplied by the third column. And the fourth variable w gets multiplied by the fourth column, giving us exactly what we have on the left side of this equation. On the right side, we have vector 6, 1, -4. Okay? So this is another way to express our linear system of equations. And so if we compare it to the linear system, the coefficients of the system are the matrix. Okay, this is just the coefficient matrix. These are the variables, x, y, z, w. And then on the other side of the equation, we have what's on the other side of the equal sign as a vector, 6, 1, negative 4. 6, 1, negative 4. Okay? You need to be able to quickly move between one equation and the other, and you need to be able to recognize that these are all different ways to express the same thing. In all these ways, we're going to be solving a linear system of equations. Now, the way we do that here is the same way we are going to do that when we have a linear combination equation or when we have a matrix equation. Okay? So to do that, we take our coefficient matrix, which is 3, negative 2, 4, 1, negative 1, 0, 5, negative 2, 2, 1, negative 1, 3, and we augment it with what's on the other side of the equal sign, which is vector 6, 1, negative 4. And then we transform the matrix into reduced row echelon form. Okay, so you need to be able to identify this matrix and be able to transform it for any way we present the system. So if we present it this way, we have our coefficient matrix, the numbers in front of the variables, and then the augmented part is the other side of the equal sign. Okay, coefficient matrix, and then the augmented part on the other side of the equal sign. Similarly for our linear combination equation, the columns that we are linearly combining are the columns of the coefficient matrix. And the vector on the other side of the equal sign is the augmented part of the matrix. Okay? And similarly for the matrix equation, the coefficient matrix is here. And on the other side, we have the augmented part of our augmented matrix. Okay, so we solve these all the same way. And we can represent the system in all these ways. Okay, so whether you have a linear equation like this, or a linear combination equation like this, or a matrix equation that looks like this, we solve it the same way. I do want to point out that we can, if we represent it this way, we could really compactly express the equation that we're dealing with. So if our coefficient matrix, if we call that matrix A, and our vector variables, vector x, and the vector on the other side of the equal sign, we'll call that vector B, then this equation becomes matrix A times vector x equals vector B. And so we've gone from expressing a linear system of equations this way to expressing the same system of linear equations this way. This is much more compact, much easier to write, and much easier to think about.